Hello. Hi. Hey. Welcome UCLA alumni and friends. My name is Dennis Hong. I'm a professor here at the Mechanical and Aerospace Engineering Department and the director of RoMeLa, the Robotics Mechanisms Laboratory at UCLA. Are you ready to see some robots?
Yeah.
Yeah, so come on in. So as you enter, you see all the awards that our students won, from best paper awards, competition awards, a lot of publicity. I'm on the cover of Forbes magazine, probably the only non-rich person on the cover. So we really started our robotics work back in 2007 with the DARPA Urban Challenge. Urban Challenge is at the time was the most difficult competition about building robotic cars. So you press start and nobody touches anything, and the robots actually drive the car, obeying all the rules of the road. So we won 3rd place in the world, and that really put us on the map. And since then, we built a robot called Charlie. It's a humanoid robot. It's considered the United States' very first humanoid, adult-sized humanoid robot, and many, many different things. And today I want to show you a lot of cool stuff. So come on in. Yep. So when you do robotics research, that doesn't necessarily mean that you build robots, but we do build robots because, of course, it's fun. But one interesting thing is, you can do robotic research and just simulation and theoretical work, but unless you really build it and test it, you don't get to really know all the details. So we focus a lot on building actual prototypes. So this is the workshop. So you can see a lot of tools. We build things. This is a new type of robotic hand that we're working on. Oh, the secret project, no. A lot of different things. So how do we actually make the robots? We have electronics and those kind of things. You probably know about 3D printing. Have you done 3D printing before? Yeah. So we do have 3D printers. So we call those additive manufacturing, which means that we add material to build the part. But many times when we make metal parts, we call it subtractive manufacturing. So I'll show you one. Ryan, do you think you can run something?
Yeah, definitely. I got something set up.
Okay, come on in. So Ryan is one of our undergraduate researchers. We have about 20-something graduate students and about 15 undergraduate researchers as well. So this is a machine called a CNC machine. So easy way to think of it is it's a robot that makes robot parts. So for example, we put this like big metal block, right? And we design all the parts using a computer, and you send that information to this machine, and this machine will cut the part like this, and these kind of parts come out. So these we use for the robot. So from this big metal block to this, right? So you call it subtractive manufacturing, from here to here. And Ryan, I think you can show us how it cuts, yeah?
So stand back a little bit, because it can be dangerous.
Safety first, always. Ryan is not controlling it. The computer is controlling all the motion, and there's a tool that spins like a drill, and it's cutting all the metal and taking away unused metal to make the part. Now, I think it's gonna take a lot of time, so let's continue the tour. All right, thanks, Ryan.
No problem.
Let's move that way. Again, be careful, there's a lot of sharp stuff around. So we have a lot of interesting robots. Probably this is the first robot that you see. Everybody knows the Luskin Center, right? It's a 5-star hotel on campus and a conference center. It's great. And this robot is called Lara, Luskin Automated Robotic Assistant. And this robot is actually permanently at the lobby of the Luskin Center. Of course, we're fixing it so it's here, but in probably a month, if you go back to the lobby, you'll see Lara. So this is a robotic platform to do many different type of research, but it actually it's a concierge. For example, if you have questions, you can ask the robot, and Lara will answer questions. At this point, we have pre-programmed questions. So for example, about me, like you're curious about the robot. What is your name?
My name is Lara, the Luskin Automated Robot Assistant. Nice to meet you.
Nice meeting you. Who created you?
I was created by RoMeLa, the Robotics Mechanisms Laboratory at UCLA, located in the engineering building right behind you.
Which is over here. Now, being all UCLA alumni and friends, I'm sure that you want to see Lara doing the 8 clap.
1, 2,
3.
6, 7, 8.
UCLA. UCLA, fight, fight, fight. Yay! We got the spirit. So at this point, there's only pre-canned questions and answers, but you can see it has microphone, has cameras, and the more we use this, it gathers more information, and we're going to add artificial intelligence. So in the future, you can actually talk to the robot, and it will give out answers. So we're very excited about Lara. And it looks cute too. So this Lara doesn't walk. As you can see, the robot is bolted to the ground. But if you want to have robots that do useful work, it needs to move. It needs to go to places. If you want to have a robot to do your dishes, take out the trash, or do work in a factory or a disaster relief, it needs to go from point A to point B. We call that problem mobility problem. The robot needs to go from point A to point B. How do we do that? Now, yeah, we can use wheels. Your car, does it have wheels or legs? Wheels, right? Because wheels are simple, they're efficient, they're great, they're low cost. But we're trying to build humanoid robots or legged robots or bipedal robots that walk like us. Why would you want to do that? Why do you think we need legged robots? If wheels are great, why legs? This is stairs. That's a great answer. If we want to have robots living with us in this environment is designed by humans for humans. Your stairs have a certain height. It's designed for a human to walk up. Your door handle is a certain height for people to open it up. So for robots to move around in this environment, we claim that the robot needs to be human shape and size. And that's why we try to build human-sized humanoid robots. And I'll show you some of our humanoid robots. Right, come on over here. Okay, cool. Right. Yeah. This one is called Darwin. It stands for Dynamic Anthropomorphic Robot with Intelligence. It's very cute. This robot is researched and developed with the fund from the National Science Foundation. Everything is a full open source robot. Middle button, right?
Yeah.
Soccer. Okay.
Start soccer demonstration. Sensor
Okay.
operation.
So this robot is fully autonomous. Just to show you, we programmed it to play a game of soccer. He likes the color red. And you can kick the ball, all right? Right foot. There you go. Hey. Do it again. You can do it. You can do it. Kick it. Kick the ball. Kick the ball. The other side. Right foot. Right foot. Yay! And if he falls down, of course he knows how to stand up back again. Right? So this is just one example. It's not just a soccer playing robot, it's an open source robot, so people can use this platform to do robotic research. If you have ideas of different type of algorithms and coding, you can use this robot platform to do experiments. Isn't that cool? Yeah, you want to, give it a, yeah.
Is there a reason why you chose that sign?
Oh, by the way, he likes you. He's looking at your, he likes red color, right? So it's like, I'm not gonna follow the ball. Which one? Oh, I like your pants. Thank you. All right, so this is Darwin.
Demonstration.
Thank you very much. So these robots are great. They're small. By the way, these are not toys. They are very expensive, right? But these small robots cannot do any useful work. We need to have big robots to do the difficult things. Yes, question?
Is there a reason why you created Darwin of that size?
Oh, yes. First of all, cost. Having big robots, very expensive, very dangerous. Like these metal beasts, when you're doing things, if it falls, it's going to be dangerous too, right? And then these kind of things, bipedal robots, they don't scale very well. So smaller robots are much easier to control with 2 legs, but when you make it taller, it doesn't scale very well. But we do need to have big robots. So what we want to show you over here is called Thor, Tactical Hazardous Operations Robot. Now we have some really strong, beefy robots, right? This robot is designed and developed for disaster relief situations. About 6 years ago in Japan, the Fukushima Daiichi, in the nuclear power plant, there was a big accident. A lot of people died, and even now it's a big problem. So when we have these kind of accidents, we need to send robots to save people's lives. Now, it's very difficult for workers to go in there to rescue people's lives because of radiation, people are gonna go. So that's why you developed this robot. So this robot can drive a car, climb ladders, use power tools, open and close valves, and all those kind of things. So at this point, it is autonomous, but today we're gonna do just remote control just to show you. I think it's gonna do some self-introduction, I think.
Good afternoon, everyone. Welcome to RoMeLa. My name is Thor, RD, Tactical Hazardous Operations Robot. Rapid deployment.
See?
I participated in the DARPA Robotics Challenge in Pomona, California. And then in July, I went to China to play in RoboCup 2015. Now, I am a 5-time world champion in RoboCup. Again, I am grateful to meet you.
Okay, thank you, Thor. So if you look at Thor, So just like a human, it needs to have sensors to gather information from the outside world. So for humans, what kind of sensors do we have? What do you use to gain information from the world? You use your eyes to see, right? Thor has this camera. He sees using the camera. He has microphones to hear, right? And also you have some sensors that you don't have in your face. Like for example, inside your ears, you have the sensor for balance. So for this robot, we have a thing called an IMU, inertial measurement unit, and we use those sensors for balance. We have force torque sensors and all those kind of things. This is a special sensor called a laser rangefinder. So what it is it shoots out a laser. And if there's an obstacle, it hits and bounces back. And it measures the time. And if you know the speed of light, and you measure time, then you can calculate the distance. So it shoots out a laser and scans the environment, and it knows the three-dimensional terrain and geometry in front of it. So it can figure out, oh, there's a box, there's something, there's a car. So we use those kind of sensors. Now, it looks like a human, right? 2 legs, torso, head, and arms and hands. It's something different from a human. Do you see anything different? What about the configuration? Is something weird over here happening?
Technically we go like this and he's going back.
Yeah, that's right. The knees bend backwards. Why would we do that? Well, this is something that we noticed by doing experiments. Originally, the knee was bended forward like this. But when we're walking upstairs, it tend to hit a lot of things. So we said, what if we invert it backwards? And hey, it works perfectly fine. And that's actually better. So that's the only reason why you bend it backwards, right? All right, so these humanoids are good, but the problem of these humanoid robots are they constantly fall down. They're slow, they're expensive, they're complicated, right? And you know, oh, do you want to make it walk? Can we? Yeah, let me show you walk it. Yeah, it walks really, really slow. Right, let's make it walk a little bit. As you'll see, it walks very slow. Oh, I'm gonna get you. No, it goes like, Terminator's coming. Oh, very slow. All right, but again, what you see over here is that this is state of the art. As I mentioned, it's slow. Josh is behind it because if it falls, he can catch it because these are very unstable. So we got a long way to go. Cool, thanks guys. All right, yes, question.
Do you guys ever study like animal movements to decide how your robots are gonna walk, or quadrupedal movement versus bipedal?
Yes, absolutely. So what we're showing right now is humanoid or bipedal locomotion. So we try to study how humans walk. We collaborate with other researchers and medical community and sports science. And also you see these 6 cameras over here, 1, 2, 3, 1, 2, 3. Like these are not security cameras. Do you know what these special cameras are used for? We call these motion capture cameras. So like in the movie industry, computer graphics, you know, probably seen actors put these like special balls, and when you move it, it captures the motion of the actor and then use that for computer-generated animation. We use these same type of cameras to study human motion and robot motion and compare that. So yes, we do study human motion for humanoid robots as well. I also collaborate with other people as well. Cool, yeah.
So you were talking about the senses.
Yes.
Would there ever be a need for him to have either a sense of smell or a sense of touch? Like to know that there's a fire or something?
Yeah, very, very good, sharp question. Yes, we do need, but I guess it depends on the situation, depending on the application. Smell is a fantastic sense. Now, for humans, it's not that sensitive, but for dogs, we still use dogs for sniffing out, you know, bombs and those kind of things because dogs have such a heightened, you know, sense of smell. So some researchers are trying to develop new type of sensors like artificial nose, and if that's available, yeah, that'll be great. Touch is actually very, very important. We also do research and touch. We put these, we call that tactile sensing on robotic hands. So when you grab things or try to pick up things, you do need to use your sense of touch. So yes, we do use skin-like sensors as well. Right, thank you so much. Yeah, so humanoid robots are great, right? We need these robots to walk and climb stairs, but they always fall down. We have a lot of visitors come to our lab and they see our robots and they're like, wow, this is cool. But after about 5 minutes, they say, Professor Hong, but how come they only walk this fast? How come they always slow down? We walk with 2 feet all the time, right? So stable, so fast, but why can't we do this with robots? Now, I can explain this to an adult or a scientist, but I had this philosophy. If I cannot explain it to a child, then probably that means that I personally don't truly understand it. So I start to do more research and try to think about fundamentally, why is it important to make robots walk with 2 feet? And I found something fascinating. Now, check this out. So, for a robot, human robot to walk like this, one of the big problem is your left leg and the right leg has the distance between them. And this is a problem. Why is that? Because your leg moves forward and backwards, right? And because of this distance, that creates this unwanted twisting motion and falls down. Now, if you look at a ballerina or doing fencing, they always walk sideways. Because if you walk sideways, everything lines up. So you don't have that twisting moments anymore. Okay, problem solved then. You make your robots always walk sideways, right? That's possible. But the problem of walking sideways is that you're not really using your knees. So we decided to do this. Okay, if you're gonna do this, let's make this forward and make it walk like this, right? It's not a humanoid form, but it's bipedal and it's stable. And thus, this robot is born. Ta-da! Oh. This robot is called Navi, or non-anthropomorphic biped, which means it's a robot with 2 legs, but it does not look anything like a human, right? So because of this is forward and backwards, by the way. The reason why you have this face is for cuteness, but also before we had this face, people thought it always walks sideways. No, this is forward and backwards, so it walks like this. Can you make it walk? Okay, so it's much more stable, it's much faster, it's low cost and lightweight, right? So it's so lightweight, this is all, right? Oh, wow. And it can walk stably. So this is I truly believe this is a breakthrough. It's a way of thinking differently, literally out of the box, and we solved a lot of problems in bipedal locomotion, right? Cool, neat stuff. All right, what can we show next? Can we do Alfred? All right, so you might ask, okay, this is great, so it walks this way, but how does it turn? Right? Or it's stable this way, but how do you guarantee stability sideways? It doesn't have anything, so thus Alfred was born. Now this is an early prototype of Alfred. Alfred stands for?
Autonomous-legged helper robot, personal helper robot with enhanced dynamics.
Cool, right. So don't think of it as a 4-leg robot. Think of it as a Navi robot with two arms. But however, we call this multimodal locomotion, which means that there's many ways of making it walk. For example, because it has 4 limbs, we call these limbs not legs because they can be used for walking, but also for manipulation, like picking things up. We can walk with four limbs, such as this. As you can expect, it walks like a 4-legged, creature, right? But if you want to make it go really fast, you can change the configuration like this, and then gallop or run like a horse, like a dog. Don't make it go too fast. We only have that. It's gonna run into you. just a little bit. Right? See? And then we're not ready to show you today, but of course, if you fold your arms like this, becomes this type of Navi top bipedal locomotion, and in the future we might be able to do like this and do like a cartwheel kind of motion. To run like this, right? So this is an early version of the robot. Cool. Thanks, Josh. All right, so this is all great. Now, one of the fundamental problems of these type of locomotion robots is that these actuators, think of it like muscles, the things that make robots move. Normally, we use electric motors with a gear. Now, 99% of the robots that exist today use these type of motors with gears, so they're very accurate. They're strong but accurate. The problem is they're very stiff, and stiffness is good if you want to do like a assembly task because the accuracy is good. But if you want to have leg locomotion, you need to have something compliant, which is springy. So it's springy. So most of the human robot walks like this, like a robot, right? That's because the actuators used are electric motors that are really stiff with gears. But what we really need are actuators that has compliance, right? Like we call it artificial muscles, like animal muscles. So we developed a new type of actuator called the bear actuator. Can we run this too? Yep. So you've seen the Navi robot. So instead of these traditional electric motors with gears, now we're replacing them using these special actuators that we developed in-house. We are very excited about this new actuator. This will enable, things that nobody's seen before. This is an early prototype. Okay, you're just gonna make it hop a little bit. Okay, jumping a little. Right? Cool. Yay. So hopping is actually very difficult to do in robotics, not necessarily because of the jumping part, but more importantly because of the landing part. Because when it lands, if you have just a regular motor with gears, when it lands, because of the impact, all the gears shatter. But because this actuator is very compliant, we can do all this stuff. What if we can have a robot that walks with 2 legs that never falls down? Or it's a robot that cannot fall down. Wouldn't that be cool? Can you have a robot that's so safe that a baby can crawl in front of it without any danger? we have built a robot that just does that. How can you do that? So we come up with all different types of creative ideas. One way of coming up with creative ideas is that we ask ourselves ridiculous, crazy questions to ourselves. And then ridiculous answer comes out, right? And sometimes those answers lead to ingenious ideas. So one day we asked ourselves, what if we can change the direction of gravity? It doesn't make any sense, but we asked those questions and ridiculous answers comes out and we came up with a robot called Baloo. Is Baloo ready? We have Baloo. Yeah, that doesn't work. It's a robot. It's a helium balloon with 2 legs. This is ridiculous, but look at this. It walks elegantly. It can climb up steps. It can climb down steps. It can jump, right? Right? Yay! And it's the world's safest robot. Yeah, you can shove it or give it a hug if you want to. Yeah. Yeah. So this is a very new concept. Nobody's tried anything like this before, right? All right. Yes.
How do you find your inspiration to think of the kinds of questions to ask?
So there's many different things. Sometimes we have a specific application like, oh, there's a disaster at a nuclear power plant. How can you build robots? So we have a problem and we need to come up with solutions. Sometimes we randomly have some kind of interesting idea for a mechanism which has no purpose or no application, right? So that idea itself has no purpose, but I have an idea notebook. I always write that on my notebook. And sometimes I have these call for proposals for research agencies. This time we need these kind of technology. I just flip through and suddenly I see a sketch like, we can use this. Then those ideas which had no value finally finds an application and that's how it comes about. So it all depends on the situation and cases. Yes?
I have 2 questions.
Yes, please.
Can it see and how can it?
Oh, can it see? So this robot currently has no sensors. So this has no intelligence. We're just remote controlling it because this is a brand new concept. We want to test if it can walk now. But yes, it will have eyes, sensors, just like the robot Thor. Eventually, it will have a computer to think.
What happens if the balloon pops?
Oh, if the balloon pops, what would happen? Now, first of all, you can blow up another one, which means that because these robots are so cheap, so low cost, like this one, it's multi-million-dollar project. If you break this, it's a big problem. Something like this, because it's so low cost, you just do another one. So low-cost robotics has a lot of value to it, right? And your question, so these type of robots solves a lot of problems. It doesn't fall down, it's fast, it's low cost, it's great, but it also creates new type of problems too. These type of robots won't be able to carry heavy things. There's a soda can, right? So it cannot carry heavy stuff, yeah. And also, this robot is not good for outdoors because in outdoors, if the wind blows, it flows around, right? So it has its limitations. We see this robot more as an information device. So it can have like a tablet with a screen. So it walks up to you, you can do like a walking kiosk, or in a factory, if there's like a gas leak, we can send these robots to take samples and sort of surveillance. So it has its own nifty type of applications. All right, so bipedal locomotions, humanoid is great, but what about biology? Like in nature, yeah, there's humans and walk with two feet, but there's different types of locomotion as well. Like insects have how many legs? 6 legs, right? So why not hexapod robots? Yes, glad that you asked. We're also working on hexapod robots. Shen, what can we show them?
So walking.
Okay.
And then changing the body orientation.
Okay, let's go down that way, if you could. Yeah, go that way. So this robot is called Sylvia. It stands for 6-legged vehicle with intelligent articulation. So it looks like a spider, but spider has how many legs? 8. So this is not a spider. It has 6 legs, right? It's omnidirectional, which means that there's no forward and backwards and sideways. It can go in different directions. Yes.
It needs 2 more legs to be a spider.
Oh, that's correct. Yeah. Yeah, and then go up. The body can go up and down, right? Down, and it can do all changes. It's good, like dancing. And we believe this is the strongest hexapod robot in the world. So can I put this weight on it, if I may? So I have a very heavy. Just a second. It's 20 kilograms, right? And it can handle very, very heavy weights. Okay, now also, this is the World's very first robot that can climb and brace between walls and climb. This might not work, but we'll try over here. So it's gonna go through this wall, this opening. So you are the very first people to see this live. We haven't shown this to anybody in person besides our researchers in our lab, right? So it's positioning itself.
But there's a pretty good chance it will fail, so.
Okay.
Sit down. Don't be too much.
You can do it, Sylvia! Oh yeah, all 6 legs are off the ground. And kind of walk up. Slowly. It is like Spider-Man.
Look up to this one.
Okay.
So we have a controller that regulates the body position, orientation. So when it climbs up, the body will be flat, so the bottom of the wall.
So it tries to maintain balance while walking up. Again, you're the very first people to see this outside of our lab. Yay, thank you. That's cool. All right, cool. I think we're done with this. Let's show the big one. So it's gonna take a few minutes to set up the large one. So meanwhile, any other questions you have about our robots or in general, anything? Yes, please.
What's your best idea that didn't work?
Best idea. We have so many ideas that never worked. The things that you see. So the interesting thing is people only want to see our successful robots, but behind these we have like 10 times more failures. So these robots that we show you, it's a multi-million-dollar project. There's only one in the world of this kind. So these prototypes are very expensive and rare. So when you do experiments, you don't want to break this, right? So you do experiments very, carefully. There's many other labs, great labs in the world, but our lab, RoMeLa at UCLA, is different from all the other labs in one sense. When you do experiments, I tell the students to make it go faster and try to lift heavier things, and I tell the students to try to break the robot. Because if your robot doesn't fall and doesn't break, you don't get to learn anything. So failure is not necessarily a bad thing. Of course, if we can avoid failure, we do. We try to. But if it fails, we want to learn from them. So failure is not a bad thing. And that answers the questions. We have 10 times more failures, and all of those failures gave us a chance to learn about things, and that led to all the success. In our lab, the greatest, most proud products from RoMeLa is not our technology, it's not our robots, it's not our publications, it's our students. I want to have students graduate from RoMeLa UCLA and go out there in the world and become engineers that will lead in the field and create technology to make the world a better place. Yes, please.
It's not a question, it's an observation.
Yes.
We were talking about pursuing ideas with no purpose.
Yes.
That's so inspirational that I think it's a message that should get out to people in all industries and all different works of life. Because we should all do that.
Yeah. Thank you so much. That's what we do. So if you look behind you, you see that wall. That's not graffiti. So that's our ideal wall. So that conference table is where we do brainstorming sessions and we write things. And you see a bunch of math equations and things. And more than half of them will probably never see the day of light of day. And but we come up with all different type of crazy ideas, and some of them lead to breakthroughs, right? That's what we do. Yes?
How do students get to work in your lab, or how do they apply?
Okay, so our lab, RoMeLa, is for research and education. It's mainly for graduate level research, funded research, but we also have a lot of undergraduate researchers. Graduate students, they come from all over the world to join our lab. Undergraduate students, they get to have a chance to get some hands-on and really learn what research is all about. Now, interestingly, our lab is very, very well known worldwide, so people want to come in our lab, especially undergraduate students. If I open my email, you'll see like more than just today, I have more than 20 emails from people who want to join our lab. Now, many times students, when they want to join our lab, they only see the fancy robots and they say, oh, if I join RoMeLa at UCLA, I'll be able to create and make these robots. And they come here, and surprisingly, many times they don't get to actually build things, but they do math and things. And some people find this fascinating. This is my thing, and they become our graduate students when they graduate. Some students find that, oh, this is not what I was expecting, this is not my cup of tea, and they leave. And that's actually not a bad thing because it's important for students to really know what they're getting into, right? But if you like robotics, this place is more fun than Disneyland. Yeah. Wasn't that cool? That robot is called Sylvia. It's a hexapod robot, the world's very first robot that can climb wall like this. We also have a larger version of the hexapod robot. It's called Hex, and it's behind you. So you probably see this, you probably didn't know it was a robot. Okay, let's make it stand up. It's huge. Whoa. So we are developing this robot for the application of demining. So after a war, there's a lot of dangerous landmines underground, right? And then many times people step on it and they get injured or killed. So we want to get rid of those landmines fully autonomously. So this is the base platform to do that. So why do you think we have 6 legs versus 2 legs? I've been talking about, oh, we need humanoid robots, all those kind of things. What advantage would 6 legs have over two legs? Yeah, balance. So if you want to walk in a real rough terrain outdoors, it's much more stable. We call it static stability because every time you have, at least feet touching on the ground. So of course, okay, it can go up, body up, right, and down, up and down, and also it can change its orientation. Whoa.
Is it also to cover like more of a distance?
Yeah, so this area is currently open because this is where all the sensors and things will go. So our vision is, it's not ready yet, but there's going to be a landmine detecting sensor. So 24/7, 360 days a day is going to be walking on a minefield. And from here, as a sensor, so it's going to be searching the ground, right? And if it finds a landmine, it's going to sit on it. Here, there's going to be a dome. So when it sits on it, the landmine is going to be inside the dome. Thus, it's now a controlled environment. No wind. Inside the dome, there's going to be lighting, so there's no shadows. And inside the dome, there's also going to be 2 robotic arms. So when it finds a landmine, it sits on it, and sends a signal to an operator. So I've done, beep, 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 beep. Oh, there's a landmine. I go to my workstation, and I tell the operator control the arms to dismantle the bomb. So that's the idea. Yeah. But what if the robot steps on the landmine? Well, is that a problem?
Yes.
It's a good thing because instead of a human, a robot explodes, who cares? We build another one, right? So if it explodes, that's a good thing. Yeah. So you've seen a lot of different shapes and sizes, and the famous architect Louis Sullivan once said, form follows function, which means that the shape of an object is dictated by what it's used for. Same thing with robots. Depending on the application, the shape and morphology and the size is all different, right? Let me show you one more robot. I don't know if it's gonna work. Again, this is also the very first time we're showing it to, is it working? All right, this robot is Pebble. Daniel, could you tell us about Pebble? What does Pebble stand for, first of all?
Pebble stands for Platform for, I think, Evolutionary Locomotion Bipedal Experiments.
Yeah, Pebble, okay. So this is just the lower body of a humanoid robot. So this actually had the whole humanoid robot, this was the early version of Thor that you've seen over there. Now, after experiments, we took it apart, so that's the lower body. We're using it for locomotion experiments, and this is the upper body separately, which we use it for something else. We'll show this in a minute, but let's show Pebble first. So this is a platform. We're trying to study many different type strategies for making robots walk like human.
Okay. I'm not holding it, it's just for safety.
Okay. So what we're going to do here is we are going to show Pebble balancing on one foot. Right?
Ooh. What you're seeing over here is all brand new. It happened in the past few days.
Wow.
Let's see.
So it might not work, which is okay. If it doesn't work, we learn from it. So.
Okay. So I'm telling it to move its weight onto the left foot, and I think if I do this, and we can actually have it.
Oh, his foot's off the ground. Okay. So these are all loose, right? So he's not supporting it.
Not supporting it. Yeah.
So even though he changes his body posture, he can still balance on one foot. Now, this is obvious for humans, but it's difficult to do in robotics. Are you going to be doing the pushing thing or no?
So we can do that too.
Okay. So that's just one demonstration of balancing on one foot. Okay. We're going to set it to a different mode this time. We call this disturbance rejection. In other words, when robot is walking, sometimes there's a wind gust or it hits to something, there's disturbances, right? And then if the robot that cannot handle it, it's gonna fall. So trying to figure out how to change its posture to get rid of the disturbances. So it uses different sensors, right?
Right, so there are sensors in the ankles that allow it to detect if something is kind of like twisting. And so with those on, the robot
Ooh.
can tell that, oh, I'm pushing here, but it'll try to go back to its original position.
So normally, if you didn't have this algorithm, when you push it, it's gonna fall forward, like a structure, right?
So you can actually like really kind of push it a lot here, and with.
Can I push it?
Yeah, sure. So
there's a limit. We push the boundaries and limit, right? Yeah.
So this was initially in Thor?
So this was a earlier version of Thor. So this is retired, and we build a new Thor. And instead of taking it apart, we actually took the lower body only and modified it for a new test platform. Yeah, recycled it. Cool. Thank you very much, Daniel. Yeah. All right. So the upper body is something different. So Netflix, there's going to be a new mini-series called Magic for Humans starting August 17th. And one of the episodes is us. Oh. So I didn't know, I don't know if you knew it, but I'm also a nearly professional magician myself and a nearly professional chef as well. I was on Master Chef USA, by the way. Yeah, season 4. Don't look me up, it's kind of embarrassing, but So there's a famous magician called Justin Willman that you probably know. So he travels around the world and visits different places. And he actually came to our lab because he wanted to learn about robotics, right? I'm not gonna spoil all the storyline, but he is a magician and he challenges us. Can you build a robot that can actually perform magic? So in 3 weeks, we challenge him and build a robot. And this was Magi. It's a robot that performs magic tricks. So we're not going to show you everything because you have to see it on TV on Netflix in August. But we're just going to show you a sneak peek of one. Oh, there we go. These are small Darwin minis. Can you say anything? Do you want to say anything about it? Yeah. Gabe.
I don't know. We're going to be doing some research using a vision system here and kind of manipulating objects and seeing how to grasp things. Yeah.
This is a comment. I like the bow tie.
You have good taste. Is a face as a move? Is a thing? What is it?
It's supposed. We can put your face on.
Oh no. Oh, okay. There you go. So you're gonna just show one
just
magic
one
trick.
Simple
trick.
Hopefully it goes well. It's hit or miss.
Yay. Okay, ball in the cup. Abracadabra. Whoa! Hey. So it's kind of a fun thing that we're doing, but it's for studying manipulation. Doing something like this is very, very difficult for robots. So this is a sensor. You know the Xbox Kinect sensor? It's actually a Kinect sensor, so it tries to identify objects and do manipulation tasks. All right? So those are all the robots that we created. There's some more, and there's some secret projects that we're not ready to unveil. But these are Darwin minis. We didn't build this, but it's based on the robot that we built, Darwin. This is actually a commercial project. Can you let some of the kids play with it? Okay. Okay, do you want to give them? You can control them. Yeah.
Probably go back.
Let's do it on the carpet over here. Yeah. Carpet, yeah. Whoa!
Oh, you exist.
Oh my god.
It's Gangnam style.
Oh! Oh, the horse stand. Oh. Yeah.
Okay. All right, you can play with it more, but again, I would like to thank you again for coming to RoMeLa, the Robotics Mechanisms Laboratory at UCLA. And I would like to give a round of applause to all of our hardworking students who set this up. Thank you so much, guys. You guys are great.